It's pretty wild when you stop and think about it. There's this incredible amount of hidden energy all around us. And I'm not talking about in batteries or power lines. I mean, it's stored inside the very stuff on your desk, the car you drive, the bridge you cross. It's this invisible potential just waiting.
I mean, take a look at these springs. We all kind of get what they do, right? They compress, they absorb a shock, and then they bounce right back. They're basically mechanical sponges for energy. But that brings up a really fascinating question.
So why is that? Why can you stretch a rubber band, but a dry twig just snaps in two? Why can a spring soak up a huge impact when a glass plate would just explode into a million pieces? Well, the answer to all of this comes down to one core concept.
We're going to pull back the curtain on this hidden potential by looking at something engineers call strain energy. And trust me, it's the absolute key to understanding why some things break and some things bounce.
Okay, so to get this, first we have to talk about work. Now, in physics, work isn't your 9-to-5 job. It's what happens when you apply a force to an object and make it move or, importantly, change its shape.
It's a really simple, logical chain of events. Just picture yourself pulling on a rubber band. Step 1, your fingers apply that force. Step 2, the rubber band stretches out, it deforms. And step 3, the effort, the work you just did pulling on it isn't gone, it's now stored inside that stretched rubber band, ready to go. And that stored energy? Well, it has a name.
And that name is strain energy. Honestly, that analogy on the slide, it's just perfect. Thinking of it as a material battery is the best way to get your head around it. When you deform a material, you're literally charging this battery, and when you let go and it snaps back to shape, that battery is discharging its energy.
So, where is this battery? What's actually happening deep inside the material to hold on to all that energy? For that, we've got to zoom in, like way in, all the way down to the atomic level.
So inside every solid thing, you've got atoms held together by bonds. You can just picture these bonds as millions of tiny, microscopic springs. Strain energy gets stored when you mess with these tiny springs in two main ways. On the left, you've got normal stress. That's just a fancy way of saying you're pulling or pushing, stretching those atomic springs apart or squishing them together. And on the right, there's shear stress. That's when you twist or slide the material, which bends the angle of those bonds. Both of these actions are basically pumping energy into the material.
Okay, so that's the tiny, microscopic view. But how do we get from atomic bonds to practical rules that engineers use every day to design things that, well, don't break? Let's see how we can actually maximize this energy storage.
Let's just take a simple metal bar. If you wanted to absorb more energy without failing, you could make it longer. That just gives you more stuff to stretch. You could also use a more elastic material, something a bit springier. But then there's this last one, the one that seems totally backwards. You can make it thinner. Wait, what? How in the world does making something thinner help it absorb more energy? Let's check out a case study that shows this perfectly.
This brings us to a classic engineering puzzle, picking the right bolt for a job that involves sudden shocks. And it's a perfect example of how the most effective design can be, well, pretty counterintuitive.
Okay, on screen we've got two high-strength steel bolts. Bolt A, on the left, is the beefy one. It's got a thick main section, what we call the shank. Bolt B, on the right, is a bit leaner. Its shank is thinner, the same diameter as the weakest part of the bolt, the threads. So here's the pop quiz. Your life depends on it. You need the bolt that can take the most sudden shock without snapping. Which one are you picking? The thick bolt A or the thinner bolt B? I mean, your gut instinct is probably screaming, thicker is stronger, pick A. But let's see what the actual analysis shows. And the results are in. The thick-shanked bolt A, it can absorb 2.26 joules of energy. But the thinner bolt B, a whopping 3.21 joules. Yeah, the thinner bolt is way better at handling an impact.
And this isn't just a tiny difference. The supposedly weaker design, Bolt B, can absorb a staggering 42% more impact energy. That is a massive, massive improvement. But why? What is going on here?
And this right here is the aha moment. With Bolt A, that super thick shank is so stiff that almost all the stretching and energy absorption gets forced into the absolute weakest part, the threads. But with Bolt B, by making the entire shank thinner, the whole length of the bolt can stretch and deform together. It acts like one long, efficient spring. It distributes that work over way more material, which lets it store far more energy before anything fails. The source material really just puts it perfectly. It's not about having brute strength in one spot, it's about having a design that lets the whole part pitch in and help absorb that energy.
And that is the huge takeaway here. Our intuition, our gut, often tells us that to make something stronger, you just add more material, make it thicker, heavier, beefier. But as we just saw, sometimes real strength comes from a smarter, more efficient design.
It kind of leaves us with this final thought to chew on. What if true resilience, whether it's in a simple bolt or a way more complex system, doesn't come from just brute force? Maybe it comes from designing things so that every single part gets to contribute its full potential to the whole.